Good afternoon, and welcome back to the last session, the last thematic panel of today. So as I was saying before, this panel will burst over the optimization and saving energy in HPC centers. And it will be chaired by Julita Corbalan, who is System Software Energy Management at Barcelona Supercomputing Center. So whenever you're ready, Julita.
Thank you, Alberto. Thank you, all of you, for being still here, okay, at that time. Let me introduce, before starting the panel, also my colleagues. I want to say thank you to them because they are coming from different data centers in Europe. So first, Benjamin Chaya from SURF in Netherlands. Cristina Manzano is from the Jülich Supercomputing Center, and Federico Tese from Chineca. So just to say a little bit more about them. Sorry, this is not mine. So Benjamin is working in the energy footprint and optimization for scientific applications at SURF, as I have commented. Federico is the HPC specialist in Chineca. He's involved in the energy efficiency and performance monitoring. And Cristina from Jülich is working involved in various European projects and is part of the core team developing and operating the LOFAR long-term archive in Jülich, in storage. Okay, so this panel will talk about energy efficiency and optimization from a point of view a little bit different from what is more common when we talk about energy efficiency and optimization. So probably most of the talks, presentations, and the work that is being done by vendors, for example, is focused on the two main areas like cooling and efficiency, energy efficiency from a hardware point of view. In this panel, we'll want to address this common goal of the energy efficiency from a software point of view. And not only that, even the four of us, we work on that topic. We work on different ways, different aspects that are complementary, okay? So for example, Benjamin is more involved in applications and having relationship with users. Cristina is more involved in the storage system. And Federico is more involved on runtime and monitoring systems, okay? In my particular case, at BSc, I am involved in the system softwares, also runtime and monitoring, but also addressing other topics like, for example, PowerCam, okay? So we will try to give you an overview of different ways, different aspects to attack this common goal. So the way we are organizing this panel is the following one. So we will spend like 20, 25 minutes. We will try to fit in this time, showing, presenting some slides and showing the experience on the different data centers and the different approaches that we are addressing. And then we will maintain like 35 minutes for an open discussion that we will answer a few questions, but of course you are open and free. And in fact, we would like you to participate and give us your opinion, okay? So what's the idea? As I have commented, what is the idea of this panel? So as I have commented, there has been energy efficiency and optimization is a hot topic today. It's very, very important. It has been addressed by all the hardware vendors, all the European projects. So we are talking on energy let's say, in all the contexts. But it has been mainly attacked, at least from the vendor's perspective, from a hardware and cooling perspective. But the software is something that we haven't success. We haven't yet convinced final users. Data center means to use libraries, monitoring system, or tools, okay? So the experience says that there is not, at that point, there is not a kind of, let me see if that works. Pointer? No? Okay, well, anyway. There is not yet a standard or a kind of tool, like for example, in job scheduling, we have Slurm or PBS, or 2, 3 system software tools that are not standard but are widely accepted. So this idea of this situation, this scenario is not existing in this topic of services and tools for energy management and power management and optimization, okay? So apart from presenting the different approaches, one of the things that we will try to answer or to comment is what could be the reason and how we can also address not only having good solutions or good tools or showing good performance tool, but also how we can convince and to reach final users, data center admins to rely or to trust us to apply these techniques that in the research context they have been much more, I would say successful, but at least we have been trying to provide good results, okay? So in the last, mainly in the last year, also in Europe, but also probably we will say the last 2 years, the electricity bill, has been one of the key reasons to pay more attention to power and energy management and optimization. It's more than management in optimization in data center, okay? So we are receiving more attention, and the data centers are starting to really consider, not only in papers, really consider the possibility of using and accepting these tools. Okay, so let me start with the few details, few ideas, and this is my area of expertise at BSc. About what we have in mind to start working at BSc Mare Nostrum 5. So Mare Nostrum 5 is still the hardware is still under the installation. In the software side, there will be several, of course, tools installed, like the scheduler, storage, and so on, as in any data center in Europe, okay? At the level of the energy management, one of the nice things from our side is that the ER is going to be installed in Mare Nostrum 5, okay? ER is a BSc developed system software. It was developed in collaboration. It was a very successful collaboration project with Lenovo, okay, with a Lenovo project. So a little bit of history is the ER software is is created in this collaboration project. Coming from this ER software, it happens an EIS spin-off, so that gives us, I commend him because that gives us the possibility to reach ER in production systems, because we found that was a limitation, because when only having research tools, it's very difficult to enter into production systems, okay? So for example, right now we have ER installed in 2 big data centers in Europe, in Supermuc Engine at Teleset, Snellius in Surf, okay? And I hope soon will be in Mare Nostrum 5 at BSc. So that has provided some experience and very, very interesting experience on that topic. So what is ER offering? So again, I will not provide you too much details, but this is the view we have, and I will show you also not only what we are doing, very, very generic, I will not go to technical details, but also what we have in mind of what should be addressed in a kind of tool as ER, for example. So on the core of ER, we have this performance and power monitoring for system management and application analysis. So it's not only power or energy, it's all the metrics from a performance point of view that we consider that we need to understand why we are consuming the power. Does it make sense? Can we manage more efficiently? Okay, so it's not only power. So these monitoring tools are used for a runtime and static analysis. So we use the metrics at runtime for optimization, but we are also reporting and showing all these metrics that we are computing at runtime for optimization to the final users and to the data center for potentially some static optimization. Using this data, we are creating some CPU, memory, and GPU frequency models that are used for our optimization algorithms. Again, I will not enter into details. The only thing more relevant is all these processes on at runtime, so there is no need of using intervention. One of our goals was to have a easy-to-use tool. Finally, we are also offering PowerCap, which is at the cluster level, and also the accounting system, which is one of the main requirements is to have this accounting to start having the understanding of what the users are doing with their jobs, the power consumption in all the nodes, and so on, okay? So partially some of these services were already provided by individual tools. One of the things in this case of this software is that the same software is providing all the services. So more or less we are providing in ER the basic requirements for a data center, like accounting, monitoring, optimization, and PowerCap. So what we have in mind for the next is what needs to be done from our side is, for example, to have, sorry, I don't see. So we want to provide support for, or be flexible enough to support any kind of architecture. We want to support also different application frameworks and workflow managers. This is something that we are still not covering, and it's one of the I will not say limitations, but one of the parts that are not still well covered for our tool. We want to participate in a definition of a standard. For example, we are involved with Federico in the Rigel project. The aim of this project is to create a kind of European power stack, okay? API, architecture, and so on. We want also to work in the interaction with other tools, okay? And very important interaction with final users, because again, we don't have this feedback from the final users to understand what they need and what is missing, so they accept this kind of tools, not only here, I mean, I think it's in general, and it's very, very important to be accepted in production to maintain the readiness, the TRS level, to guarantee there are no an impact on the production systems. So, based on our experience, there are like different questions that we will comment later. It's not to talk about that right now. But for example, we will need, the experience says that we will need more collaboration from the hardware side. We will not address that part, but we will need more collaboration from them, because it's very difficult, it's very complex to get access to frequency management, power management. It's really, really complex, so that it's limited the type of work that we can do. And also it will be very important that in the community we are able to understand what is really needed. It's a problem of robustness, it's a problem of being easy to use. These are the kind of answers that we need to understand and have an answer for everything. So let me give the word to Benjamin Jaja from SURF.
Hi, thank you for inviting me. My name is Ben Chaya. Yeah, I'm from SURF, that's the Dutch National Supercomputing Center. And basically, Julita has asked me to kind of prepare 3 basic slides about what we do at SURF and yeah, how we kind of track the energy usage and the energy optimization of software on SURF, on Snellius, our super. Yeah. So maybe for those of you who are maybe not familiar, Snellius is a tier 1 system, so it is not the biggest, most powerful system. It is around 6 petaflops at the moment, like I think most supercomputers, or at least Snellius is a phased system. And it's a bit heterogeneous, so we have a CPU partition, we have a GPU partition, we have a high memory partition. But what I'm brought here is just kind of give you a characteristic of our machine, that we have about 500 Rome CPU nodes and about 70 NVIDIA A100 nodes. But the 2 pie charts I'm showing you, one is performance and one is energy usage. And the most basic thing is how much energy usage the CPU partition takes up compared to the GPU partition. So you more or less get the same amount of compute using GPU with 1/5 of the energy envelope. So I think my first slide is architecture. So that is generally the most important thing, and kind of the more traditional thing is trying to port your code to a more energy efficient architecture. I get these things wrong 3 times. But we work closely with Julita, and we have EAR enabled on Snellius. And what this allows you to do is gather metrics about your application. So what I'm showing you here on the left panel is a traditional performance strong scaling plot. It's of a lattice Boltzmann code. On the y-axis, you have GLUPS, giga lattice updates per second, but that just means performance. And the scaling across our full system. So here you see generally pretty good scaling, if I can call it that way. But along with using EAR enabling, you're able to gather hardware counters and metrics of your application, so you can also see how it scales with energy. So you can see as we kind of depart from this linear scaling of this code, we also depart from a linear scaling in energy. So this top point that I'm showing you here was a full system, full CPU partition run. And this took about 30 kilowatt hours of energy. It ran for 9 minutes. So that at the pricing time of the Netherlands, at that time, that particular job that cost 9 minutes to run costs about €9 in energy cost. So that's kind of a real amount of energy. Yeah, just some fun statistics about that job. It had enough energy to run for 9 minutes on the machine. It would drive an average electric car about 150 kilometers. So I think the point I want to get across here is, first, we want to introduce energy as a metric right next to performance, because those things are very closely related, and making your energy footprint of your application aware. So just making the users know how our application is doing energy-wise. And I pressed the wrong button again. And then I want to end on what we're kind of trying to do at the moment. So right now we're trying to, monitor the application, but we also want to optimize for it. And in EAR, there are 2 policies, more or less. What I'm showing you here on the left panel is phase space between main memory bandwidth and cycles per instruction. So if something has really low cycles per instruction, it's generally CPU intensive. And basically, we have a phase space of applications that populate this phase space. So we kind of try to make decisions on what EAR policy fits the application best in order to save energy the most. So what I'm showing you on the right panel is one application, again, this Palabos application, and showing you the different policies that may affect this application and the energy savings that you get. So here we see generally about 10% energy savings, while only being less than 5% in actual runtime savings. So you do see performance degradation, but you try to balance the performance degradation with the actual energy envelope that your application uses. So yeah, this is more or less what we're focused on at SURF, and I can press the wrong button again. Yeah.
Okay. Yeah, like this. So, Julita already introduced me. I'm Cristina Manzano. I'm working in the Jülich Supercomputing Center in the Technical Services and the name, so I have to say. Before it was called Technology Department, that's easier. And now I'm leading a small team, Technical Services team. And I'm also working in a community service, operating and developing for a LOFA community, which is a radio astronomy, long-term archive. I want to give you a quick glance of my workplace. So on the left side, this is the Forschungszentrum campus, which is quite large. There are many different institutes in the fields in information, energy, and bioeconomy. On the right side, this is 2 of the buildings of the JSC, of the Jülich Supercomputing Center. Its focus is high-performance computing. That's why I chose to add this picture there with this dual-track approach, which we follow at the center. So basically, we have general-purpose systems like the Eureka DC and the Jewels cluster, and highly scalable systems like the Jewels booster, which is GPU-based, but I'm mentioning it a bit later on. This is kind of the summary of what I want to say here. So we have realized that we need a holistic approach in order to optimize the energy usage. So we need to address every part, every level. So I'm going to give you a few examples of what things that we are doing at the strategy at each level. So system level, one of the thing that Jülich is focusing is in provide energy efficient system architectures. This is where this dual track approach comes into play. So we have modular systems with modules which are highly interconnected, and the applications run in the different modules depending on their demands. At a data center level, one thing I want to mention is the cooling. Since last year, we have an hybrid warm water cooling system for Eureka DC and the Jewels booster. And in this system, there's these 3 towers, which you see in the picture, on top of the building with these dry coolers. And in this setup, you have basically like 2 water circuits. Like one is the primary one, which is the one which actually cools down the electronics, and the secondary one, which evaporates the heat, dissipates the heat to the environment. We have heat exchangers between them. One of them is, we have 3 of them. One is connected to the dry coolers, and second one is only as backup, connected to the chilled central supply water. And the third one is in a testing phase, and I'm telling you now more about it. At a campus level, there is the whole Forschungszentrum campus. There is this big project going on, the Living Lab Energy Campus. Its goal is to develop some campus-wide energy management platform with different energy supply systems which are connected. It has different pilots. One of them consists in reusing the supercomputer's waste heat to heat buildings. So the buildings in the campus. So this is where this third heat exchanger is being used and tested at the moment. Looking a bit into the future, we are going to have next year already, if everything runs as scheduled, the Jupiter, which is going to be the first European exascale system. I think it was mentioned before this morning by someone. So about Jupiter, what I can say, it's going to follow as well this modular supercomputer architecture that I mentioned. It's going to be hosted not in a concrete data center like typical ones, but it's going to be modular one with some prefabricated modules. And long-term idea is to be able to heat all the buildings in the campus and probably in the near houses outside with the heat waste of Jupiter. And my second to last slide is actually a bit more closer to my field, to storage. We have in the ULIST a multi-tier storage cluster for the supercomputers. So we have, you see there on the right side, up this pyramid, we have a large pool of archive space based on tape libraries, which is cheap in terms of energy and money, but it's quite slow. And then we have really fast layers, the one on top, flash and expensive, but the applications can make use of one or the other depending on their use case or the ones in between. And a last example of this smart use of resources, in this case of storage, is this long-term archive that we have for the radio astronomy community. We are storing their data on the tape libraries, but we have a cache layer on top. This is spinning disk based, and which is quite small in comparison. We are talking here about roughly 1 petabyte disk, spinning disk, versus more than 20 petabyte on tape. So this cache is used in a smart way only when it's needed for hot data, when they need to process data, for example. And that was it actually from my side. I hope it was interesting. Thank you Thank you very much.
Good afternoon, everyone, and thank you to whoever remained here for the last panel of the day. I will say just a few words about what tools at Cineca we are using or trying to use to tackle the problem of performance and energy efficiency. So, okay. We have seen that HPC data centers today are very useful. They help us to resolve a lot of problems in very different topics and research areas. However, they have some drawbacks. They are very large industrial plant hungry for energy and power. Nowadays we speak about 10, 20 megawatts. And they are very delicate, okay? So what we can do to try to take these two drawbacks? Okay, that depends by the point of view at which you see the two problems. Okay, usually there are 3 organizations that handles data from the facility system, which are user support, system, sysadmin, and facility manager. From that point of view, we would like to have a holistic vision of the overall system, being able also to detect and predict anomalies just in time and to avoid the problem. On a second point of view, we can see the user approach. Okay, we would like to let user understand how their applications are performing from an energy and power point of view. So regarding the first goal, so the holistic vision of the overall system, at Cineca we are using Hexamon. Hexamon is a tool developed by University of Bologna, Unibo, and it's a project in collaboration with them. It is a data collection and analysis platform oriented to manage very big amount of data. It is very versatile, it can be distributed, it's scalar, it can get information from different plugins, very different plugins from the hardware level to the software level. And it can be used, for example, for real-time anomaly detection, predictive maintenance, or having a digital representation of the system. Digital twins is something that's quite on fire nowadays, no? as a topic. Okay. For the analysis and for the reduction of energy consumption for user application, we can present you Countdown. It's a tool developed in Cineca, and Countdown is a reactive mechanism which can reduce the frequency entering the MPI communication phases and restoring it at the maximum as possible at the end of the communication. I mean, you just don't have to do pretty much anything to use, just use LD preload, and he will do the job for you. Now I will present you some works under development. Something has been already done, but there is a lot under development, and that's the first things. We would like to, regarding the user approach to their energy consumption, we would like to let them have a graphical representation of how their application performed. To do that, we created this conjunction among Hexamon and Countdown, creating some dashboard specific for a job, from which, for example, you can get information about, of course, about performance evaluation of your job, like flops, bandwidth, instruction retired, stuff like that, MPI process, etc. But also you can have an idea about the power and energy consumption of your application at runtime. I mean, that's a post-mortem image. I'm sorry, this is not very high resolution, but that's what I had. Other things that there are among development are, as I said, detect anomalies and faults to prevent them. So the idea is once Hexamon will be installed on Leonardo, obtain all the information that he can get from the plugins and the sensor that he has, and training a deep learning model, and in this way close the circle and predict if there are some faults in the data center, like for example some thermal hazard prediction. We can see here a problem due to the augment of the temperature of the inlet, and so the idea is to predict and can be ready to not have it during the productivity of the system. I think that I finished. It was like 5 minutes, right? More or less. Yeah, okay, cool. Thank you.
Can you hear? Yes, sorry. Thank you, Federico, Cristina, Ben. So the idea was to show you a little bit the topics that we are working, and also, for example, Cristina and Ben and also Federico has presented a few images and numbers of the data centers, okay? So at the end, we are representing 4 very important data centers in Europe, no? And we are addressing from the point of view of the software. So I have several questions that I would like to address to them, but of course, I invite you to participate and give your opinion, because at the end it's a panel and we would like to be as much interactive as possible, okay? So one of the questions I already have, let's say, in my list is the strategy or the way in the different data centers where I have been involved or working or collaborating with, I have seen the strategy they have followed, asking always to let the user, the final users, to do, I will say, what they want. I mean, run at the CPU frequency or GPU frequency they prefer. They are not, it's not at all mandatory or even recommended or even, let's say, motivated the utilization of any optimization tool, neither at runtime, neither statically. But in some other cases, for example, at LSET, in SuperMIC and U, they are much more restrictive, and they are forcing the users to run at a specific CPU frequency, which is not turbo, no? Because in general, in most of the data centers, the CPU frequency selected is turbo. So I would like to know your personal opinion, and also in the audience, of course, if you think in the current times where energy is so expensive, where there are so limitations in power, I mean, in the current circumstances, even if they are taking into account the architectures and the cooling are again and again more efficient, I agree on that. But do you think that is from an energy efficiency point of view, the best strategy to continue allowing the user, the final users, the ones that in some way take the decision of what they do in terms of power and energy, or should we start being more active on, I will not say forcing them, but at least motivating them or even forcing them to use runtime tools or specific CPU frequencies or to show a certain energy efficiency? What do you think? Ben, thank you.
Yeah, so right now, to give you context, it's an opt-in strategy at Snellius. So the energy optimization is there for them to use. It's quite simple to use, but they have to opt in to use it. And I would say, as my experience, probably 0.01% of users are aware of it and would like to use it. So it's, for me, this topic is becoming much more popular, and it is much more on a high level, just a general user who is doing data analysis of some population in the Netherlands that's not necessarily high performance computing but uses Snellius. They would generally be interested, but then they would have no idea. They're somewhat comfortable with Slurm, and that's about their level. So given this past year of experience with EAR on our systems, I would go for an opt-out situation where we do some optimization by default. Yeah, and if it's a really robust user that knows what they're doing, they can always change and opt out of this situation. But yeah, that's my personal feeling on it.
Thank you, Ben. Federico or Cristina, do you want to?
Yeah, I agree. It's an interesting question. I mean, in Ulish also the users can adjust Slurm when they choose. They can select clock frequency, and yeah. So how you motivate them to really make use of this and not just go for full power and that's it. I guess you can give feedback and show them some kind of dashboard, something where they see what they are doing. So maybe that's the way to go. In a similar way, I can mention from this Living Lab Energy campus that I mentioned before, there is also a dashboard which they are implementing where you can see your office and how much energy you are consuming, the temperature when you open the windows or close them. They are trying to gamify the whole thing, so you are aware of you are letting the window too long open in winter, maybe just close it. And it's a really small thing. I mean, this is really peanuts in comparison to what of these monsters, these supercomputers use, but it's kind of a way. You need to kind of show what, look, this is what you are, your footprint, what you are doing with your job. So I don't know, I mean, it's still open.
Okay, it works. I don't know if, I mean, take a decision from the facility level for the user could be, at this moment, as useful as motivating the user. Because, for example, all these tools that we have seen, they have, of course, at least very little, but very little overhead that augment the time to solution of application running on our system. And if there is no common layer for energy-saving libraries or tools, I'm speaking about European level, where at this moment you can apply for core hours almost everywhere in Europe, okay? A normal user would go where his application run faster, and also in this way you cannot guarantee also reproducibility of the data at the end of his run on different HPC center. I think instead that they should be motivated to use the best tool as possible to reduce their energy and power usage compared to the overhead that they are getting. I'm speaking about time to solution brutally, because I think that at this moment is the most important thing for me for the user. So you have to motivate it, as we to motivate them, and maybe let them understand in a graphic way how badly or how well they perform on an average level. And if they performed well at the end of 1 year, for example, they maybe could get some extra core hours on the system for free, and in this way they could be motivated to maybe spending a little bit of time more to get their important results. Of course, definitely they are important because, but saving the environment and also saving a little bit of money for the hosting entities on which they are running the application.
Thank you, Sergi.
Yeah, Julita. I think there should be intervention of the data center because they have the global picture, they have the OPEX responsibility, and for me, a good example is the motorways, not the Spanish or the Italian motorways, but the German motorways. You have no speed limit in many options on the motorway, but where there is you have to brake, they break down. For sure, they don't care. They drive on the right. If there is an accident and there is a limitation to go and speeding at 100 or 80, they go. They didn't ask. They simply go on that speed because this is someone doing the analysis and considering this is good for the whole population. So we are high-performance computing centers, so we have to go fastest, the fastest the better, but someone has to take responsibility. And I was having a question to Ben on this matter. So are the users ready to be allocated in batches instead of hours? Then they can make the decisions. But of course, they will complicate things. So there should be someone, answering to Julita, taking care of the global view of the OPEX, because that's a budget limit on that.
Thank you, Sergi. Yeah, in fact, this question about the motivation, it's something that I was wondering if motivation means that we must do more tutorial, more workshops, more, I don't know, or motivation means that there is some reward, no? That is what like you were saying, no? If you do that, you will get more core hours, or the motivation is that the allocation is not time, it's power, so when you finish, it's finished, no? But then it is a data center decision, no? It's not because sometimes it seems that the data center belongs to the user, no? It's like they must be able to do what they want. I think it's not the case. They are not the owners of the data center. They are not paying the electricity bill, no? But I have the feeling, maybe you can say something to that, no, Sergi, that it's very difficult to convince, no, the people that has to take or has the capability to take the decisions in a data center to change the way things has been working, always working in a given way, like allocating hours, for example, and to take that decision to switch or to change and to do in a different way, no? It's because it's not really so important, because in fact my feeling is that we are talking about power, energy, but nobody cares, in fact, about that. For example, in the European projects, there is always a requirement to show power metrics or energy metrics, but we just compute at the end. I mean, just to do the deliverable, but people, it's not really, they don't care, no? So, do you really think it's important enough to take, for example, that decision that you were just suggesting, on not so much in real life? It was for you the question, but it's really open, but maybe you can give your point of view, which is really important.
I have a comment on that. So my feeling is that generally researchers are absolutely willing, and they ask about it all the time. In the Dutch perspective, we have the acronym is NWO, that's the funding body that funds research. And it's well defined what an SBU is and how much an SBU costs in euros. So we define projects, here are your allotment of SBUs, and this is kind of standard practice. But it's really unknown, and I do believe it's unknown how much energy usage of an average project is. I think that's a question mark. So I believe it's our responsibility to bring awareness to that. And that's two things. One, telling them about it, but also normalizing a metric so you understand, oh, okay, 20 million joules, that's about the same as 1 million SBUs. So it's about kind of bringing everyone into the same reference point, and we all understand what a joule is or what a kilowatt hour is, and kind of normalizing that metric to be like, oh, that's about a year's worth of research. So yeah. So for me, I think that's the biggest motivation, is people are generally interested, they really care about it, and they would be willing to sacrifice their wall time of their application, but it's about kind of agreeing on a metric and everyone understands, like a liter of gas costs this much. It's along those same lines.
Yeah, here. We have time, well, we don't really have time, but we'll just do like one last question, if you're okay with it, because we really need to wrap this up because the minors room visits are starting in 3 minutes or something. So we have one question right here.
Yeah, it's kind of a question and advertisement as well, because, well, my name is Manuel Jimenez de Castro. I'm from the Earth Science department at the BSc. And at the Earth Science community, it's pretty standard to have the SYPD, which is simulated years per day for each of the models. We also compute the joules per day, per year that it costs to run the simulation, to raise awareness to the scientists with the energy consumption as well. So, I mean, maybe we're like the 1%, the 0.1% of the people that are like, well, we're calculating this for the scientists so they can take decisions on top of that to see if their model actually is more energetic. Because also a friend of, like a colleague of us, using that statistics, built a methodology to run the models in the most efficient way, energy-wise. So, I mean, there is a little bit from, and all of that with the sense of, you know, CO2 emissions, greenhouse emissions, not as much as like the energy bill that Sergi has to pay for us, but more so about the CO2 that's getting, you know, emitted to power all of these massive HPC centers.
Thank you. So, Alberto, should we finish then? Okay. So thank you very much, all of you, for your attention and participation.